Series. Loosely put, a series is the sum of the terms in a sequence, which is denoted using the sigma notation that n go from 1 to infinity a sub n. We determine the conversion of the series by looking at the partial sum s sub n, where s sub n is the sum a sub 1 plus a sub 2 all the way to a sub n. This is the sum of the first n terms. If the limits at n go to infinity of s sub n, which is the partial sum, is finite, then we say that the series converges. Thus, to determine the conversion of the series, we consider the sequence of the partial sums s sub n. S sub n is the sum a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n minus 1 plus a sub n, which can be denoted using the sum of the first n minus 1 term plus the a sub n term. The non-terminating decimal 0.9 bar is 0.999 ... with infinitely many nines. This is 0.9 plus 0.09 plus 0.009 plus 0.0009 plus, and so on. But 0.9 is 9 over 10, 0.09 is 9 over 100, 0.009 is 9 over 1000, then 9 over 10,000, and so on. Rewriting this, we see that this is 9 over 10 to the 1 power plus 9 over 10 squared plus 9 over 10 cubed plus 9 over 10 to the 4th power plus 9 over 10 to the 4th, and the n terms is 9 over 10 to the n power plus, and so on. This is an infinite sum because we add infinitely many terms. The terms in this sum is what we call the terms of the sequence, where a sub 1 is 9 over 10, a sub 2 is 9 over 10 squared, and a sub n is 9 over 10 to the n power. The infinite sums of this type is called the infinite series. An infinite series is basically the sum of infinitely many terms. As of now, we won't be able to determine the conversion of this series, even though we know that this sequence converges, but we can't say anything about the series. The sequence a sub n has the closed form a sub n equals 9 over 10 to the n, and yes, at n go to infinity, a sub n go to 0, but that has nothing to do with the series. To determine whether the series converges or diverges, we would need to look at the partial sum. The partial sum is the sum of the first n terms. The partial sum is denoted using s sub n, and it is the sum. We use the sigma notation to denote the sum. N go from 1 to n of a sub n. In this case, s sub 1 is the first term only, which is 9 over 10. S sub 2, the partial sum of the first two terms, is the sum of a sub 1 and a sub 2. This is 9 over 10 plus 9 over 10 squared. And we know that this is 0.99. S sub 3 is the sum of the first three terms, a sub 1 plus a sub 2 plus a sub 3. And this is 9 over 10 plus 9 over 10 squared plus 9 over 10 cubed, and we know that this is 0.999. S sub 4 is the sum of the first four terms, a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, and this is 0.9999. The sum S sub n, the partial sum, is therefore the sum a sub 1 plus a sub 2 all the way to a sub n, and this can be denoted as S sub n equals S sub n minus 1 plus A sub n, because S sub n is A sub 1 plus A sub 2 plus dot 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 plus A sub n minus 1 plus A sub n, and the sum of the first n terms is the sum of the first n minus 1 terms plus the n term. This is the partial sum. In this particular example, if we use these partial sums and form a sequence, then we see that the sequence consists of 0.9, 0.99, 0.999, and so on. This is a list of numbers, so this is a sequence, but it is a sequence of the partial sum S sub n. We can see that this sequence, it converges to the number 1, so we can only speculate that the given sum, or the number 0.9999, is 1.